Most importantly, I hope as you go through this user meeting, you take away the message that we're here to serve you, and I am here to serve you. We need your help. We will do this together and deliver great science for all the world as well as for Sweden. But we're now at the point where we can offer you 10 beamlines with baseline capabilities, and we'll expand on those as we go forward. I just would like also to share one milestone from last June, which I think communicates the sense of excitement that we have for you and what we're offering you. Short pulse facility charge with time is shown here in the top. The 3 GeV ring current with time, nearly 250 milliamps, and about the same in the 1.5 GeV ring. And you see not only this very stable delivery of beam, but essentially flat current. The little wiggles are the top-up operation as charge is injected in every so often to keep the average current the same. That keeps the optics warm, it keeps the beamline stable, everything runs very smoothly in this mode. On the right you see in green indications for the open shutters of 11 beamlines simultaneously. This paper just appeared on September 20th in Nature Communications. It's one of the 2 very nice highlights that appeared last week, in fact, at Biomax, or for Biomax, where the structure CSX1-CoA4 complex was determined by protein crystallography methods at the Biomax beamline, structural biology beamline, by Montoya and colleagues. What's really nice about this, if you're familiar with the idea of this concept of CRISPR, which is a sequence of DNA fragments that reflect on the ability of prokaryotes, bacteria and archaea, to defend against viral attacks. Controlling this, and what this method shows, or this work shows, is that these active sites, both the catalytic site and this binding pocket within the structure, could enable exquisite control of the system for possible biotechnological applications in the future. So we're very happy to see a nice publication come out on a high-level journal of this category. You can expect more to follow. In parallel, some very nice work has come out of Nanomax. Remember, these are our first 2 beamlines. It takes some time, typically a few years, before work appears in print after the experiments have been conducted. But this also just came out, I think about 3 weeks ago, in Crystals, where a team from Lund University has been studying by a multimodal method the various structural imperfections, in particular the local strain inside of indium phosphide nanowires that they fabricated, heterostructured nanowires. The experiment requires focusing the beam down to a sub-100 nanometer spot, hard X-ray beam, measuring in both X-ray fluorescence, transmission, scanning transmission mode, the induced current by X-ray beam induced current with electrodes on the sample, and most importantly, X-ray diffraction going to a Bragg peak of this crystalline or multicrystalline wire, and watching how imperfections in the Bragg peak, asymmetries in the Bragg peak, tell you about the strain as you scan across this wire. So it's proof of principle. The next step is really to understand how that information can be used to control these devices as you fabricate them, but it's working beautifully and the data quality is excellent.